Hope you people are able to see my screen, right?
Yes, ma'am.
Okay. So in the last class, we have seen a direct sequence PET spectrum with BPSK. Okay, why we are going with the modulation scheme? Because if we want to transmit it for the longer distance, we have to, we cannot directly transmit because of so many parameters. Okay, so what we need to do, we need to modulate the signal and then transmit it so that the reception will be proper. Reception in the sense the received signal will be properly decoded at the receiver end. Okay, so that is the reason here what we are doing, we are using the spread spectrum technique. Okay, which is nothing but we are multiplying B of t signal. Okay, whatever data signal we have, that B of t signal will be multiplied with PN sequence. Okay, PN sequence, pseudo noise sequence or pseudo random sequence. Okay, so the resultant one, M of t is nothing but the resultant one. Okay, so that is modulated and it is sent to the transmitter, through the transmitter to the receiver. Okay, so we have seen all the diagram related or the waveforms related to related to the transmitter. So I had B of t. B of t is nothing but this signal. Okay, so B of t is nothing but your data signal. Okay, generally we were writing in all the previous cases 0 1 0 1 1 0 1 something like this. Okay, so this is nothing but your data sequence. So here I've just taken for only 1 and 0. Okay, just to show you, I have just taken only 1 and 0. With and the time duration of this data sequence is TB seconds. TB seconds. So within this TB seconds, I should have the PN sequence. Okay, within this TB seconds, I should within 1 bit duration, I should have all the PN sequence. So here, if you just observe 1 0 0 1 1. Okay, 1 2 3 4 5 5 bits. Okay, the PN sequence is generated by as 5 bits. Okay, so this 5 bits should occupy 1 TB. Okay, 1 TB in the sense 1 bit duration. Okay, so after that again what happens, it will be repeating. Okay, the same thing will repeat again because PN sequence is the periodic sequence. Now what we did, we have multiplied B of t with C of t, so that this is what the resultant waveform. Now again resultant waveform we have represented as CNRZ polar. What it will do, it will give plus root TB for your 1, and it will give minus root TB for 0. Okay, so we have taken this equation and we need to modulate it. Okay, so to modulate it, I'm using the carrier with frequency FC. This is what the signal, carrier signal that I'm using. So this is the carrier with frequency FC. Now what I'm doing, I have to represent the modulated signal. So modulated signal in the sense, this S of t, this signal is nothing but S of t signal. This S of t will get multiplied with phi of t, so that I'll get X of t. X of t is nothing but S of t multiplied with phi of t. From the block diagram, see, I am not writing the equations as on my own. This is what the block diagram, from the block diagram only I am representing everything. Okay, so when you multiply carrier with this S of t, this is how the waveform will be. So if you just observe, this is 1 1 0 0 1 1 0 1 1 0 0. So this is what the waveform. Okay, so for 1 there is no phase shift. Okay, for 0 there is a phase shift. This is how we were doing the BPSK as well. Okay, the BPSK without any spread spectrum, we have already seen BPSK modulator and demodulator. So this is the same as that. Okay, only difference here is B of t. There B of t directly we were modulating, but here what we are doing, we are multiplying this B of t with C of t and then we are modulating it. That is the only difference. Okay, so here I can say that the input waveform is getting modulated twice. Okay, one by using C of t PN sequence and the other one by using BPSK. Okay, so you can just first what you can do is you can first B of t, if I have B of t first you can modulate and then multiply with C of t. Anything is same only. B of t first modulate it Okay, and then the modulated signal you can multiply it with C of t. Okay, anything is fine because it is just the linear operation. You can just change the order. Okay. So this is all we have seen with respect to the, so the same thing I have also shown you in terms of in the frequency domain as well. So this is a B of f spectrum, C of f spectrum, and this is M of f spectrum. Okay, so here what you are doing, B of f is nothing but like its bandwidth is very less. Okay, now what we are doing, we are spreading it by using C of f. Okay, so if you just observe, this M of f is nothing but C of f, M of f is almost equivalent to C of f only. Okay, so M of f, I've got the spectrum in this way. If you just observe B of t is getting multiplied with C of t, so that its spectrum M of f is spreaded. This spreaded signal I'll be transmitting it through the channel. Okay, so I've already explained you why we need to spread the signal. Okay, the reason why we are spreading the signal is if any interference signal, okay, wantedly if anybody is want to convey the wrong information, if they are trying to add that information in the channel, then what will happen because of the spread spectrum technique? We will not be able to get that noise signal or the interference signal, whatever interference signal that is there, since we are spreading and transmitting it. So at the receiver, it will despread. When it is despreading, what will happen? The noise or the interference will be eliminated. Okay. So here again, we have already seen a formula which is nothing but the processing gain. Processing gain was given by TB by TC. Okay, the same TB by TC, if you take this, it will give me some integer value. That integer I'm just representing it with LC. That's it. Okay, it is also equal to N. PG is equal to TB by TC is equal to LC is equal to N. LC is nothing but some integer. That's it. Okay, so now this is all related to the transmitter. Now we'll go with the receiver. Okay, receiver of DSSS with Bpsk. So here what I need to do, I've got the I have spreaded the signal and then I've modulated it. Now what I need to do, I need to despread the signal and at the same time I need to demodulate it as well. Okay, so let me consider I am receiving Y of t, okay, from the channel. Okay, so what will happen first, the transmitter will send X of t. X of t, it will get multiplied with some noise signal, and let me consider I am getting it as Y of t. Okay, I of t. Okay, so let me consider my output here is Y of t. So that this Y of t will be received by the receiver. So that is what I have taken here. Y of t is the received signal from the channel. Okay, so first what I need to do, I need to despread it. Again here also it is a linear operation. First you can demodulate and then despread, or despread and demodulate. Anything is same. Okay, so I need to despread it. Despread it in the sense we know very well whatever PN sequence that we were generating at the transmitter end. Here we were generating the C of t, right? So whatever C of t we were generating, here also we need to use the same C of t. That is what the advantage. If the C of t is not matching, then you will not be able to despread the signal properly. So PN sequence generator. PN sequence generator. Okay, so here what will happen, Y of t will get multiplied with C of t, so that the despreading will happen. Now what I need to do, I need to give it to the coherent detector. Coherent detector or demodulator. Coherent detector or demodulator, which is nothing but here I am using Bpsk, so Bpsk demodulator. Okay, and here I am saying that it is coherent. Coherent because whatever carrier I'll be using at the transmitter end, the same carrier I'll also use here. So carrier, local carrier. Okay, the same carrier should be used here also. And this carrier, whatever we are using in the receiver, it should be synchronized with the transmitter. Okay, then what I'll do, I'll give it to the sampler. Okay, then sampler output. Here let me consider I'm getting R of t as my output. So R is the sampling output. So that I'll give it to the decision making device. Decision making device. Okay, so it will be compared with VTH. Okay, and if R, what is R is the input to the decision making device. If R is greater than VTH, then the decision will be in favor of symbol 1. If R is less than VTH, then the decision will be in favor of symbol 0. So this is what the final estimate. Okay, let me write it as B cap of t. This is the final estimated signal. Okay, so this is all related to the receiver. See here what it is doing, it is desplitting the data here. The desplitted data is given to the modulator. Okay, modulator here, coherent detector in the sense whatever carrier you will be using at the transmitter, you can you have to use the same carrier at the receiver end as well. Okay, or if you want to go with the non-coherent methods, then you need to use the masked filter. Okay, masked filter is nothing but using that also you'll be able to demodulate the signal. Okay, so coherent detector, and here specifically Bpsk demodulator, and then it is given to the sampler. This is nothing but the sampler. Because why I'm sampling it is this R of t, whatever I'm getting, it is again the continuous signal. Okay, so I need to sample it and then I'll get R. So that R is given to the decision making device. This decision making device will compare R with VTH, and if VTH value is less than R, then the symbol will be in favor of 1. If R is less than VTH, then the symbol will be in favor of 0. So this is what the receiver. So in the exam, this question is very important. Either you take in the case of internal also, external also, they'll definitely ask you explain the generation and the detection. Explain the generation, or they may even ask us transmitter and detection, or they may ask you receiver of DSSS system. Okay, in that case you need to explain whatever the transmitter part I have explained you with the diagrams. Okay, and then you need to explain the receiver part with the diagrams. Okay, so this is a very important question. Okay, so hope this is clear to all of you, right? Is it clear to all of you how the transmitter DSSS transmitter and receiver is working is fine? No, let me go with, see here I have taken the transmitter and I have taken the receiver, but I have not explained you if there is any interference. Okay, interference, I have just told you that I have just written it, no, somewhere here. No, here I have written. See, I am saying that some jamming signal J of t is added in the channel. This is your channel, so this will get added in the channel. So Y of t is the received signal. So what happens? How we are able to demodulate it? This is what we need to check here. Okay, so for that, let me just take the heading as effect of despreading on a narrowband interference. This is one more important question. In the exam, they may ask you, explain the effect of despreading on a narrowband interference in direct sequence spread spectrum. Okay, direct sequence spread spectrum. Okay, see whatever we are studying, it is in DSSS, direct sequence spread spectrum. Okay, so here what he is saying is what is the effect of despreading on the narrowband interference in DSSS. See what he means to ask here is, see I have told you that if X of t is the transmitted signal, this is what the transmitted signal, I'll draw the block diagram, don't worry, let me give you an idea. So x of t is the transmitted signal. At the channel, what it will do, it will add some jamming signal, and then this signal is transmitted. Y of t is transmitted. So the receiver, what it will do, it will take this y of t and it has to despread it, and that's what I've told you. Here I'm multiplying it with c of t. Where is it? Here. We are despreading it. So what is that effect? So, and again I have told you that whatever interference signal that I'm adding at the channel, this jamming signal characteristics will be same as your B of t. It means that even the bandwidth will remain same as your B of t. Okay, such signals will be introduced by the people who want to send the fake information. Okay, so the y of t is given to the receiver. So after receiving this y of t, how it is able to despread the signal and how we are able to get back the original signal. That is what this question is all about, and it is very, very important. Okay, despreading the signal is very, very important. So let me first give you the block diagram. Same thing, whatever we have seen before, the same thing I will elaborate and draw. In this is like all transmitter, channel, receiver, everything I'll draw here. So first I have Bpsk modulator. That's what I've told you. Either you can first modulate the signal and then spread it, or spread the signal and modulate. Anything is same only. Okay, so here let me write it as Bpsk modulator. Then carrier, local carrier is given here. Carrier is nothing but root 2 by TB cos 2 pi FCT. Okay, that is given to the product modulator. Bpsk is nothing but, it is nothing but the product modulator. And then this output, okay, whatever output I am getting here, that I am give to the again multiplier, where the C of t will get multiplied with S of t. Okay, then we'll give it to the, then I'll get the output, which is nothing but X of t. Okay, so this is transmitted. See, whatever I have from here to here, it is nothing but the transmitter diagram. Okay, transmitter diagram. Then I'll give it to the channel. Okay, channel, it's nothing but it will add j of t to the incoming signal. X of t is coming here, it will add j of t to that, and so that my resultant output will be y of t. So y of t is given to the multiplier, where y of t will get multiplied with c of t. Okay, this c of t is nothing but the PN sequence. How I'm getting this PN sequence? From the PN sequence generator. PN sequence generator. Okay, from this I'll get C of t. Okay, that C of t, this I have to give it to the coherent detector. Okay, coherent detector, as you know, if you can recall, you can just recall Bpsk coherent detector. So what we did, we have given it to the multiplier, and the multiplier output is given it to the integrator 0 to TB dt, and then I'll get some output. That output should be given to the low pass filter. See this here, this itself will act as a low pass filter. This integrator itself will act as low pass filter. Then we have to give it to the sampler. Okay, so this is your sampler. Let me draw it a little small because I have little more big diagram. The output should be given to the coherent detector. So coherent detector, I'll have the product modulator, and then from the product modulator output I need to give it to the integrator, then to the sampler. Okay, here it is sampler, then to the decision making device, and then finally based on this the output will be determined. So here product modulator, I have to use the same carrier in the sense root 2 by TB cos 2 pi FCT. Whatever carrier I'll be using at the transmitter end, the same carrier should be used at the receiver end as well. Okay, only then you'll be able to get the signal properly, or you can use the masked filter. Anything is Fine. Here specifically we are using coherent detector. This is coherent detector. Okay, so again we need to analyze this. Let me consider the output here is nothing but u of t. U of t is the output here. Output of this y of t is nothing but u of t. U of t is given to the product modulator, so that I'll get z of t. Z of t is given here, so that I'll get r of t. R of t is given to the sampler, so that I'll get r. R is given to the decision making device, where it will be compared with the threshold value, and if r greater than VTH, then the decision will be in favor of symbol 1, and r less than VTH, it will be in favor of symbol 0. Symbol 0. Okay, so again same analysis, but here what I'll do, I will in the previous case in the receiver, here I have not explained you what will be the output, all that I have not explained here. So now what I'll do, I'll explain it in detail. Okay, so first what is happening, S of t is nothing but B of t into root 2 by at the transmitter end. See, whatever equation I'm writing, it is at the transmitter end. This entire thing is receiver. Okay, I'm writing at the transmitter end. S of t is nothing but B of t. See, S of t is nothing but B of t, and I'm giving it to the product modulator. Bpsk will have the product modulator. It will just multiply both of them and give the output. So product modulator. And B of t value will be equal to plus EB or minus EB. Okay, root 2 by TB cos 2 pi FCT. This is what your S of t value. And this S of t is getting multiplied with C of t, so that I'll get X of t. So X of t is nothing but S of t multiplied with C of t, which is nothing but S of t. S of t is nothing but B of t root 2 by TB cos 2 pi FCT into C of t. Okay, so this is what your X of t. This X of t is given to the channel. So at the channel, what will happen? X of t will get added with J of t. So that my output here is Y of t. So I need to get Y of t equation. So Y of t is nothing but X of t plus J of t. Both will get added here. This is plus and this is also plus. Both will get added. So X of t is nothing but B of t into C of t root 2 by TB cos 2 pi FCT plus J of t. This is what your Y of t equation. Now Y of t is given to the receiver. Okay, so this is what the receiver. So in the receiver, the first step is what is happening. It is getting multiplied. Y of t is getting multiplied with C of t, so that my output will be U of t. Okay, receiver. At the receiver end, what is happening? Y of t is getting multiplied with C of t, so that my output is nothing but U of t. Okay, just see the block diagram. Y of t is the input to the product modulator multiplier here. So Y of t will get multiplied with C of t, so that it will give U of t. This U of t will get multiplied with root 2 by TB cos 2 pi FCT, so that it will give Z of t. Okay, so let me write the equation. And Y of t is nothing but X of t. No, it is nothing but B of t. This equation I'll write here. B of t into C of t root 2 by TB cos 2 pi FCT plus J of t. This entire thing is nothing but Y of t equation into C of t. This is what your U of t. So now U of t is given to the multiplier again. Once again we are giving U of t to the multiplier. Multiplier here, what it is nothing but the coherent detector. So what it will do? It will multiply, U of t will get multiplied with root 2 by TB cos 2 pi FCT, and it is then integrated. What is it? Z of t. Z of t is nothing but u of t multiplied with root 2 by tb cos 2 pi fct. So z of t will be equal to u of t. U of t is nothing but b of t into c of t root 2 by tb cos 2 pi fct plus these two will get multiplied, no? Okay, plus j of t into c of t here, the same equation, u of t equation I have represented again, into root 2 by tb cos 2 pi fct. Okay, so this is what you have z of t. So z of t is equal to, now multiply c of t root 2 by tb cos 2 pi fct, multiply to this term also, this term also. So it will be b of t c square of t root 2 by tb cos 2 pi fct, root 2 by tb cos 2 pi fct, it will be 2 by tb cos 2 pi fct, cos square 2 pi fct. Okay, plus j of t into c of t root 2 by tb cos 2 pi fct. Okay, so now what will happen? This c square of t is nothing but 1, you already know. Okay, so z of t will be nothing but b of t into b of t by tb, 2 cos square 2 pi fct, I can write it as 1 plus cos 4 pi fct. Okay, 2 cos square 2 theta or cos square 2 theta can be represented as 1 plus cos theta divided by 2. The same thing I have written here. 1 plus cos, here it is 2 theta. Okay. Cos square theta can be represented as 1 plus cos 2 theta by 2. Okay, so the same thing I have represented here. So here I have 2 cos square theta. In place of theta you have 2 pi fct. So it is 1 plus cos 2 into theta. Theta value is 2 pi fct. Okay, plus j of t into c of t root 2 by tb cos 2 pi fct. Okay, now you multiply this inside. So z of t is equal to b of t by tb plus b of t by tb into cos 4 pi fct plus j of t into c of t into root 2 by tb cos 2 pi fct. Okay, so now we are passing it through the integrator. Integrator will work as low pass filter. So if you just observe, this is a high frequency component and even this is high frequenzy component. So here z of t will be nothing. So this is passed through this z of t is passed through the low pass filter, so that I'll get r of t. R of t will have only b of t by tb. This will be eliminated because it is high frequency component. See here j of t is getting multiplied with c of t, so it is spreading this. This j of t is getting spreaded. So it is again becoming wideband signal. So wideband signals will not be passed through the low pass filter. So r of t will be equal to b of t by tb. Now what we are doing, we are sampling it so that I'll get r. Okay, so I'm getting r. So r of t is passed through the sampler first, so that I'll get r. Then it is given to the decision making device. Okay, decision device, which will be compared with VTH. So if r greater than VTH, symbol 1, r less than VTH, symbol 0. So this is how the despreading is happening. Okay, so here since we are passing it through the low pass filter, it will not allow high frequency components, but instead it will allow only the low frequency components. Because of this, what is happening, the jamming signal, whatever jamming signal you are it's getting added in the channel, that is eliminated. Okay, when you are despreading the data itself, it is getting eliminated. So that is what the despreading of data. So in the exam, if they ask you related to this despreading effect of explain the effect of despreading on a narrowband interference in DSSS, then you need to draw this block diagram and explain everything with respect to the equations as well. Okay, so hope this is clear to all of you. Same thing, like if you just correlate this with the DSSS transmitter and receiver, it is the same thing, but here I have explained you with respect to the equations as well. Okay, so whenever they are asking you with respect to this splitting, you need to write all this. Okay, hope this is clear to all of you. Is it clear to all of you? Fine. Now, we've already seen some of the performance parameters, like processing gain. Processing gain we have seen. Like that, you have three different performance parameters. So even in the exam, they may ask you explain the performance parameters of DSSS system. So in that case, you need to write all this performance parameters of DSSS system. Okay, so you have three performance parameters. The first one is, which we already know, processing gain, which is given by PG. PG is nothing but bandwidth of spreaded signal divided by bandwidth of unspreaded signal. So bandwidth of spreaded signal is 1 by TC. Bandwidth of unspreaded signal, it is 1 by TB. So it is nothing but TB by TC. It is also equal to LC, which is an integer, which is also equal to N, the length of the PN sequence. Okay, so this is what the first parameter. Okay, and coming to the second parameter, which is here we need not derive it. We just need the equation related to that. Okay, that is nothing but, see here also we are using the modulation, demodulation, everything is happening. So there is probability of error. Okay, because here the decision, here if you just observe, I have the decision device and I need to decide whether the received symbol is 1 or 0. Okay, so maybe there may be some errors happening while making the decision. Okay, so we need to also have the probability of error for DSS Bpsk system. Okay, so here I'll directly give you the formula. Okay, it is nothing but PE. PE is equal to 1/2 ERFC of root EB by PN into TC. What is PN? I'll tell you. Okay, so this is the PE of DSSS Bpsk. Okay, so here EZ is nothing but energy per bit. Okay, and TC is nothing but the time period of the PN sequence. Okay, and PN is nothing but average noise interference power. Okay, so P is nothing but power. Okay, and it is given as N. Here what is the noise I have introduced? Interference signal. Okay, so PN is nothing but the average noise interference power. Okay, so this is the equation of probability of error with respect to DSSS Bpsk system. Okay, it is a Bpsk system, but we are using the spread spectrum techniques. That is the thing. Okay, in this, so here what we'll do here, whatever equation I've taken, it is DSSS Bpsk. Now let me consider I am not modulating it. Sorry, I'm not spreading it. So I'll have for the Bpsk system without DSSS, we know that the probability of error is given by 1/2 ERFC into root EB by N0. root EB by N naught. Okay, so this I'll consider as equation 1. This I'll consider as equation 1 and this I'll consider as equation 2. This is with spreading techniques. This is without spreading. This we have derived, but here you need not derive. Okay, you can directly remember this equation. Okay, here according to your syllabus you need not derive. You have to just know the probability of error. Okay, in the probability of error with DSSS, EB is fine. Okay, it is nothing but energy per bit. Okay, and P and TC are coming into picture. Okay, TC is nothing but the chip duration. PN is nothing but the average noise interference power. P indicates power. So N suffix N indicates it is the noise interference power. Okay, and now if you compare equation 1 and equation 2, then if you just observe half error function, in the numerator here also you have EB, here also you have EB, in the denominator you have N naught, so I can write as N naught is equal to PN TC. Okay, N naught, whatever, this N naught is nothing but the power spectral density of additive white Gaussian noise. Okay, if you just recall, this N naught is nothing but power spectral density of additive half of, because N naught by 2 is power spectral density of your additive white Gaussian noise. So here it is N naught, just N naught. So it is half of power spectral density of additive white Gaussian noise. Okay, so here I could give the relationship between the N naught, PN and TC, or if I want to find the noise power, average noise power, I can write as N naught by TC. Okay, so all these equations are important when it comes to the problems. Okay, so you need to see whichever I'm making it as box. Okay, all that equations you can make a note of it so that it will help you for your this one, for your problem solving. Okay, now the last parameter, jamming margin. Okay, jamming margin. Jamming margin in the sense from the name itself it says that how much jamming can be introduced. Okay, so that will be given by the jamming margin, and generally this jamming margin is nothing but the ratio of Pn by PR. PR is nothing but the average power of received signal. Okay, this Pn is nothing but the average power of what is that noise interference signal. Okay, so let me just write this equation. We already know that Pn is nothing but N naught by Tc. Okay, we'll just try to derive this in terms of propagation processing gain, and in terms of what is it, power spectral density. Power spectral density of additive white Gaussian noise. Okay, so let me derive this jamming margin in terms of Pg and power spectral density. Okay, it's not divided by. Okay, I will just rearrange the terms so that I will have this jamming margin in terms of Pg and PSD. So why it is required is for problems. Okay, to solve the problems you need it. Okay, so that is the reason. We will just try to find the jamming margin in terms of power spectral density and the Pg. Okay, and you already know what is propagation gain. Propagation gain is nothing but Tb by Tc. Okay, Tb by Tc, and here what is that, energy per bit. Energy per bit, EB, is given as the power noise power, what is it, signal power, which is nothing but PR into TB. Okay, PR into TB. So this we have already seen, EB is equal to PR into TB. So for this what I'll do, I'll multiply, I'll divide both the sides with N naught. So EB by N naught, so PR TB by N naught. Okay. And you know that